Binomial distribution or a binomial experiment has very specific characteristics and qualities. And if all those qualities and characteristics are met, then we can consider it a binomial distribution. If they are not, then you can't. Okay? So keep that in mind. So we have 4 requirements for an experiment to be a binomial one. And we'll go through those one at a time and talk about what that all means and how to evaluate it. So the first thing that must be true in order for a distribution to be binomial or the experiment to be a binomial one. Each trial can only have 2 outcomes, success or failure. Okay? Like for example, when we flip a coin, there are only 2 outcomes, heads or tails. And if we wanted to know how many tails we were going to get, the tails would be considered the success. Getting a heads would be considered a failure. And we'll talk more about that here in a second. The second quality is there must be a fixed number of trials. So you can't perform the experiment, infinitely or as long as you want. You have to be told or you have to decide that there are this many trials, period. And you can't deviate from that.
Are you recording this?
Next, the outcomes of each trial must be independent of each other. So what happens in trial number 5 cannot affect what happens in trial number 7. Okay? They are all independent, meaning the probability of the success for each trial remains the same through each trial. The probability of a failure through each trial remains the same through the rest of the trials. It can't change. And the probability of success must remain the same for each trial, which is similar to 3. Okay? The probability in trial 4 is not affected by what happened in trial 3. Therefore, the probability of success in trial 1, in trial 2, in trial 10, trial 15, the probability of success will remain the same the entire experiment. If all 4 of these conditions are met, then you're dealing with a binomial experiment, and you can use the math that I'm about to show you and consider it a binomial distribution. Okay? And the math is a little different than what we've been doing earlier in this chapter. So let's look at 3 examples. All right? Go ahead and take a picture of that. Go ahead and take a picture of that, and then we're going to decide if these 3 experiments are binomial experiments. So what we really want to do here is we want to go through the 4 different conditions, and if all 4 of them are met, then we can say it's a binomial experiment. So A, 1/3 of households in the U.S. have a computer. 200 households are randomly selected, and a count is made of the number with a computer. Okay? So let's start with the success versus failure. Okay? What would be the success? What would we consider a success for this problem? Having a computer. The failure would be not having a computer. So there are 2 outcomes. Either they have a computer or they don't. So that part's met. There has to be a fixed number of trials. Is that determined?
Yes.
How many?
200.
200 households. Okay? Does the house on the corner having a computer impact the house next door to it?
No.
No, they are independent of each other. Okay? This would be considered binomial. Okay? It meets the requirements. It meets the conditions. Okay? Alright, B. 5 cards are randomly selected without replacement from a 52 card deck. Each card is checked to determine if it's red.
Not.
Probability of success.
No, it's
So the success is what?
If it's red.
If it's red. Failure, it would be black. Okay? Is there a fixed number of trials?
No.
Yes.
How many cards are selected? 5. So both of those are true so far. Okay? Are they independent events?
No.
What makes them not independent?
Because they are not replaced.
Without replacement. Okay? Which means they don't put the card back in the deck when you draw a new one. Okay, without replacement means once you pull a card out, it's out and doesn't go back in. So it's not independent, and the probability of success will not stay the same. Okay, if that said with replacement instead, then it would be fine. It would be binomial. Okay, but because it says not or without replacement, this is not binomial. So the work in the math that I'm going to show you today and tomorrow is not going to apply to a situation like this. You could still find the probability, you just can't consider it a binomial experiment and use the math that I'm going to show you. Last one, a die is rolled until a 6 appears.
Not binomial.
Until 5.
Until a 5 appears, sorry. So it's either,
No, it's not.
what's a success?
5.
Getting a 5. What's a failure?
Any other number.
1, 2, 3, 4,
5, 6, 7, 8, 9.
1, 2.
You can't get a 7, 8, or a 9 on a die.
And there's no.
Okay, so it's either 5 or not 5. Okay? There's not, we don't know how many times we're going to roll it. So there's not a fixed number of trials. Okay, so this also is not binomial.
Independent trials though, right?
Yes, so if we would have said a die is rolled 10 times, and we wanted to know how many times 5 appeared, that would be one thing. But because there's this unknown, it can't be a binomial experiment because it's not a fixed number of trials.
There's more than one.
On to some more things here. Okay, a binomial distribution, the outcomes of a binomial experiment and the corresponding probabilities of these outcomes. Okay, what this really means is there's a way to find the probability of those outcomes using, once we know it's a binomial distribution, using a specific formula. And that formula is this.
What the?
And I will explain all of this in a second, but go ahead and write it down. We can use this probability, instead of having to find the probability of each trial and multiplying that all out and going at it that way, we can determine what the probability of a specific outcome is if it's in a binomial experiment by using this formula. Now, let me talk about what some of these things mean, and I'm going to define them all for you. This means probability, okay? I need to tell you about n and x and p and q. So those are the next things we need to know. So these are what those 4 variables stand for. So the x is the number of successes. That's the key. The number of successes. N is the number of trials. The probability of success. And then the probability of failure. Since there are only 2 possible outcomes, success or failure, that makes the probability of success and the probability of failure complementary. So if I know, for example, the probability of success, I can find the probability of failure, and vice versa.
Why? Because you just subtract it from 100.
Subtract it from 100% or 1. Okay, so the probability of failure is just 1 minus the probability of success. They are complementary events. Probabilities, sorry.
So this is like the P's and Q's.
P's and Q's, yep. So if you know the probability of failure, you can find the probability of success. Subtract it from 1. And vice versa. X is the number of successes. N is the number of trials. Okay? And that information will be given to you in the problem. Alright? Most of the time. Today what we're going to do is work through a situation that doesn't have context, just to get you used to using the formula. And tomorrow we'll put some context to it and make more sense of it. I could have just as easily said P equals 1 minus Q. Okay? Either way, they are complementary events. Okay, so depending on the problem, what they give us, they may give us the probability of success. Then we have to find the probability of failure, or they may give us the probability of failure, and we have to find the probability of success. It depends on the specific problem. Okay? So, here is the type of problem, again, and all we're going to do for the rest of this class is use the formula knowing that I have this. Okay? So, again, there's no context here. We know that the number of trials is 9. The number of successes is 2. The probability of success is 0.42. Okay, what else do I need in order to use the formula?
The failure.
I need to know the probability of failure. Okay, so what is the probability of failure going to be?
5, 8.
Okay, so Q is going to equal 0.58. I have everything I need. So here's what this problem would be saying. We're conducting this binomial experiment. It's going to have 9 trials. We want to know what the probability of having exactly 2 successes are. That's what we're going to find out. Okay.
I have a question.
So yeah, the formula tells us, all right, and so I'm just going to go ahead and plug all that in. Here's what's nice, okay? This is just a combination of 9 choose 2. All right, our probability of success, we want to have 2 successes. And in the formula it said n minus x over here. Just know that these two things, these two powers have to add up to the total number of trials. Because we have a specified number of successes, therefore there must be a specified number of failures. Okay? Now, at this point, you should know how to plug this into your calculator, and then you just have to multiply this all out and see what you get, and that will tell you the probability. Take a look. So, now, it's very likely that you entered all of this into your calculator anyway, which I'm not going to get hung up about, okay? You should have gotten 0.14. How many had that? Okay, good. So that's where I'm going to stop today, all right? Tomorrow we're going to apply this and actually have context to a binomial experiment and show you how to do it so that we're in good shape. I want to explain a little bit about this formula though real quick. This means the number of different ways you can have successes, because in 9 trials we don't know when the successes occur. They could happen in trial 1 and trial 2 and not happen for the rest of the way. They could happen in 2 and 5 and not happen the rest of the way. So what this number does is account for the number of different possibilities of where those successes can occur. Okay? And so then it's just a matter of saying, okay, 2 successes, now you kind of think of it in slots. There's 2 successes, 7 failures, and then the different ways that those combinations could occur. Right? That's what the formula is really saying.